Okay, hi everyone. I'm Nils from the Barkhausen Institut in Dresden, Germany. And in this talk, I will present one of the research projects that we are doing at the Barkhausen Institut, which is building a modular and secure system architecture for the Internet of Things. Let me start with the institute itself. So the Barkhausen Institut was founded at the end of 2017, and we are now about 30 people. We are doing research on low latency and secure IoT systems, focusing not only on research but also on demonstrators. So we want to actually build what we are proposing and also show that to the general public. And the Barkhausen Institut consists of six groups. So we have the wireless group, who is looking into wireless communication protocols, for example. The radio frequency design group is building the communication chips, the real hardware. Then we have a privacy team looking into privacy and security issues. The lab team is building demonstrators. And then we have the two last teams here who are relevant today. So we have the MPSOC team who is building the hardware platform, and then the operating system team, where I'm a member of, that is building the operating system that runs on this hardware platform. Okay, then let me go to the motivation of this project. So we expect many different IoT devices, or Internet of Things devices in the future. And we interpret IoT here very broadly so that we basically speak just of connected devices. So it can be anything from a simple light bulb or a washing machine, an agricultural machine, Industry 4.0 or cars, infrastructure, all kinds of different devices that are connected to each other. So it's always a kind of processor and a communication device, and with this they are connected to the internet. And this is also one of the problems or the challenges in this area, that we have devices that are both now connected to the internet and typically to also to the physical world. And because of that, we need to be really careful what we do, and security and safety is really important. The other point that's important is modularity, because we will have these many different devices that all have have some similarities. So they typically all have a processor, maybe an accelerator, communication device, and different software components running on top of that. And therefore, I think having a toolbox that you can pick components from and then just build one of these IoT systems without having to reinvent everything all the time is really important as well. Okay, but what is the problem that we have today? So of course these devices consist of hardware and software. Let me start with the software part here. So one big problem in software today that we have is complexity. So if we, for example, look at current operating systems, they are huge and typically also monolithic. That means it's one big blob of software that is running in the privileged CPU mode, and that means that it can do everything. And that also means that an attacker that finds one single bug in this huge code base, which is not that hard, can do everything as soon as it has exploited this bug. And this makes these systems really vulnerable. One solution that has been proposed quite a while ago already are microkernel-based systems, where the idea is that you split up this huge monolithic blob into multiple pieces and you isolate these pieces from each other. And a recent study has looked through all the critical CVEs of Linux that have been found over the years, and the study has found that in 96% of the cases, a microkernel-based system could have at least reduced the severity of these CVEs, because in that case, the bug would have happened in one of these isolated components, and therefore it would be confined within this component. So the attacker would need another bug in order to cause harm to other parts of the system. The study also showed that in 40% of the cases, a microkernel-based system could have even completely eliminated the CVE. So that means microkernel-based systems are a good alternative, and we should build at least critical systems in that way. However, the system, of course, also has hardware. And I think today, if people think about the trusted computing base, so the amount of stuff that you have to trust in order to get a certain functionality, they only think of software, and the hardware seems to be implicitly trusted. And I think this is a bad idea. because hardware is also complex today. So we have, for example, various third-party components that are typically integrated by the system integrator to build one device out of that. And that could be a modem, it could be an accelerator, like a machine learning accelerator or a GPU or similar things. It could also be just a core. And of course, the system integrator cannot just build all of these components by himself, because that would be too much effort and too time consuming. Therefore, we have to take them from third-party vendors, but of course we shouldn't trust these third-party vendors. And currently this is often done. So currently there is often no isolation between these different components. They are just integrated into a network on chip, for example, and then everybody can do everything. And we have seen that it actually happens in practice with this Broadcom incident a couple of years ago, where a bug in the Wi-Fi chip allowed a remote attacker to completely take over the system. So this is actually a real problem. Another problem in terms of hardware complexity are, at least in the past 2 years, I think that's got a lot of attention, are the side channel issues in the complex modern general purpose cores that we have. We have so far, I checked that again, 20 known attacks, but we are still counting, right? So there might be further attacks that are found. All of these attacks basically allow the attacker to leak private data from other applications, from the operating system or other sources, from virtual machines, for example, SGX enclaves, whatever. And sometimes they bypass with that all the security measures of the core. So like user kernel mode or SGX or virtual machine isolation, for example. Of course, there are mitigations, but these are also complex and they are also costly. So this is not really a good solution, I think. Also, the point is these security holes are not new. They have been lurking in the CPUs for many, many years. And the reason why they are found so late, I think, is also because the complexity of the cores. That just there are not many people that actually can oversee all of these different parts of the core and how they can interact with each other and what can happen if this and that is done and so on. So this seems to be a real problem, and therefore this raises the question whether we should still trust these complex cores to properly enforce boundaries or isolation between different software components running on top of them. So as you can see, we actually have similar problems in both hardware and software because both are complex, and also we have third-party components. So we have applications that we download from the internet and then want to execute as software, and we also have third-party components that we want to integrate in our hardware platform. So it looks a bit similar, and therefore the question that we are asking is, shouldn't we apply the same apparently well-working mechanisms from software, that we split up things into components and then isolate these from each other, to hardware as well? So how does that look like? Let's assume we have a bunch of different processing elements like general purpose cores, but also signal processing cores, or a TPU for machine learning, or a fixed function accelerator for FFT, let's say. And we integrate all of these different processing elements into a network on chip. And now the first idea of this M3 system architecture that I'm proposing here is that we add a new hardware component next to each of these processing elements, which is called Trusted Communication Unit, or TCU for short. And at first, the TCU acts as a uniform interface to these potentially very different processing elements here. Second of all, and this also allows us to, for the rest of the talk, basically forget about these potentially very different processing elements. We just call them PEs, and we now have a bunch of tiles in the system, each consisting of a PE and a Trusted Communication Unit, or TCU. And as the name suggests, the TCU is a communication device, so you can have communication channels between these tiles. But these tiles are actually isolated by default. And this is because for the PE, the only way to talk to other tiles is the TCU. And therefore, at the TCU, we can control the tile-to-tile interaction. And this allows us to integrate also untrusted PEs here into the system, like a modem or an accelerator or some core. And we don't have to worry too much about the impact on the rest of the system, because we can control its communication channels to other tiles. In terms of the software or the operating system, to be precise, it works like that. So we have the kernel running on a dedicated kernel tile here. So it's not as in many other operating systems that the kernel is running everywhere on all cores in the system. In this case, it's just running on this one core, on this one kernel tile, as we call that. And the applications are running on the user tiles, the remaining tiles in the system. And the kernel tile is remotely controlling these user tiles where the applications are running. And most importantly, it's configuring these communication channels between tiles. So the idea is, by default, all user tiles are isolated from each other. And then selectively, we can enable communication channels between these user tiles by letting the kernel configure one of these communication channels. Okay, so let's look a bit more into detail into this communication. So the TCU-based communication works upon endpoints. So each TCU has a set of endpoints, and each of these endpoints can be configured to different kinds of endpoints. So it can be configured to a memory endpoint, which you can see in this example here, where this user tile having this TCU can use this memory endpoint to access a piece of memory in DRAM. It could also be a memory area in a different tile, but this is not shown here in this example. The other type of communication channel that we have is a message passing channel. For that, we have a receive endpoint at the receiver and a send endpoint at the sender. And this allows the sender to send a message over to the receiver, and the receiver can also reply on this message to send some information back to the sender. And this is, of course, important for remote procedure calls or the inter-process communication that is very heavily used in microkernel-based systems, where we have different components communicating with each other. And therefore, we have this as a first-class feature in the TCU, that we can have, for example, a client and a server on different tiles, and then they can communicate back and forth with these communication channels. Okay, then let's take a closer look at the operating system. So it's a microkernel-based system, as motivated before. It's called M3, which is short for either microkernel-based system for heterogeneous mini-cores, or alternatively L4 ±1, because it's inspired by the L4 microkernel, but it's implemented from scratch in Rust and C++. And since it's a microkernel-based system, that means that the complex components or the actual functionality of the operating system is not implemented in the kernel itself, but it's implemented as separate and isolated user components. So in this case, that means that drivers, file systems, network stacks, and so on are running on the user tiles and not on the kernel tile. Yeah, the kernel is mostly responsible for managing the permissions in the system and creating these communication channels. And this is done using capabilities because this allows us to have a fine-grained control of these permissions in the system. The enforcement of these permissions is actually done by the TCU. So, for example, if we have a memory endpoint that gives an application access to memory, and this is configured to be read-only, then the TCU will enforce that the user application cannot write to that. And similarly, for message passing channels, we have a credit system to prevent denial of service attacks, and also the TCU will here enforce that if you don't have credits, you cannot send a message. Another interesting fact here is that the kernel is actually independent of the other tiles. For example, if the file system M3FS here is implemented on a normal general purpose core or is implemented on an FPGA, for the kernel that doesn't really make a difference. So the kernel mostly cares about the TCUs and their communication channels, and that gives the system design a lot of freedom for the implementation of these other components in the system. So let me give you an example about the message passing, and in this case system calls, because since the kernel is running somewhere else on a different core here, on a different tile, of course we cannot use the normal approach for system calls where we just have a magic instruction that takes us from user mode to kernel mode, but instead we use message passing for that. So the kernel will have a dedicated receive endpoint for system calls, and as soon as an application starts on a user tile, it will create a send endpoint that is connected to this receive endpoint at the kernel tile. And if the application wants to do a system call, it prepares the message in memory, and then it instructs the TCU to use the send endpoint to send the message over the network and chip to the kernel tile, and then the kernel will receive the message, first the TCU receives the message, will then put it into the corresponding free slot in the receive buffer, and then the kernel can look at that and can handle the message and can also use the reply feature later to send a reply back to the application. And this is of course also the way how message passing based communication between user tiles works. In terms of prototype platforms, we at first used Gem5. So we have a model for the TCU for Gem5, and this is our way to prototype the system and figure out how well things work and how exactly we want to build things and so on. We also are working on an FPGA-based prototype. So the hardware team at the Barkhausen Institut is building the TCU in hardware. Yeah, so for the Gem5 prototype, I added a model for the TCU to Gem5. And to simulate the system, we represent each tile as a system object and connect those with a non-coherent crossbar. So it should be a NOC actually, but at the moment we still use that non-coherent crossbar, also because the tiles are not coherent in our system. We use full system mode because we want to run the operating system ourselves, of course, so M3. And we have a custom loader to load the kernel on the kernel tile and so on. In terms of ISAs, we support x86, ARMv7 and RISC-V at the moment, but for the hardware implementation we use just RISC-V for the openness and the simplicity of this ISA. Yeah, we also have support for accelerators. So a while ago I added Aladdin-based fixed function accelerators or support for that to Gem5, so that we also have the opportunity to play around with that. So what we can do with that is that we can build systems like this. So we have a bunch of tiles integrated with this non-coherent crossbar, and each tile can be configured differently. So for example, we can have a RISC-V tile with a cache, and then in this case the TCU would be connected to the L2 crossbar that you can see between the core and the TCU. And with that the TCU can access the memory of the core and vice versa. We also can integrate DRAMs as a tile. And as I said, we support accelerators. For that reason, we also have the opportunity to have an internal scratchpad memory instead of caches, which is often preferred by accelerators. And of course, the accelerator could also be a RISC-V core, as you can see on the bottom right here. Yeah, in terms of this Gem5 prototyping, we discovered that RISC-V was only supported in system emulation mode so far, and for our project we need full system mode, and also we want to have virtual memory support, and therefore in this process we added SV39 paging according to the privileged ISA, the current version of the privileged ISA instruction set for RISC-V, and this fortunately brings us pretty close to running Linux on RISC-V, on Gem5. So in summary, both hardware and software is complex, and we believe for security critical devices, as we are targeting here, we need not only a modular but also a secure approach. And therefore we are using a tile-based architecture with a trusted communication unit per tile for communication control, and we have a microkernel-based system on top. And this gives us pluggable and isolated hardware and software components to build such security critical IoT devices. Both the operating system and the Gem5 extensions are open source, so you can find them at these GitHub repositories, although I have to admit that these are a bit outdated, so the internal version that we are working on at the moment is not public yet, but we will publish that eventually. And with that, thanks for your attention.